Alright, this was a quiz on radical and exponential expressions, and we really found out that those two things were different forms of the same thing, but so that's what we will be exploring in this lesson. Alright, we learned that if we are going to write a radical expression in exponential form, it's going to be like this. Alright, this index we can think of as a root, and this exponent, of course, is a power. So when we rewrite this in exponential form, it is always going to be in the form power over root as far as the exponent goes. So applying that to this problem, if we think power over root, 5 is the power, 6 is the root. So this would be x to the 5/6 power. Okay, so there's your answer to number 1. Same thing with number 2. It does have that 1 over the top of it, so that'll just stay there. But power over root. Now the power is a 1. You could think of this as w to the first power. And the root is 3, so this will be w to the 1/3 power. And you can just leave it like this. Or if you took the extra step of understanding that this is w to the negative 1/3 power, that's also great. Okay, because that negative exponent would drop you down to the denominator, so you can see that those are the same. So going in the other direction, rewriting in radical form, just remember power over root. So that means 4 is the power and 3 is the root. Okay, so let's start with the root actually. So there's my m. If 3 is the root, that means we have the cube root of m. 4 is the power, so we can put to the 4th power. Please remember that it doesn't matter whether you put the power inside the radical or outside the radical. Either way, just as good. Okay, now this one, to rewrite this in radical form, it's going to be very necessary that we think about this negative exponent and remember that that means that we need to drop this down to the denominator. So this will become 1 over a to the 1/2 power. Once we have that, then just remember that this is power over root. So there's the 1. And so let's get this started. Actually, let me make that a little bigger. Okay, so this is the power, this is the root. Well, the 1/2 power would be the second root, but we don't actually write the 2. It's just assumed to be 2 if you don't put a number there. So 1/2 power is just the same as the square root. And of course we don't need a to the 1 power. So that's it for number 4. Number 5. For number 5, we just need to do the 3rd power to both of these things on the inside. So this will become x to the 3rd power. Now when you raise a power to a power, you multiply. So this will be y to the 6th power. Now looking at number 6, I see that negative exponent, and we've learned that anytime you see a negative exponent, that means you're on the wrong side of the fraction line. So that is going to have to drop down. Alright, the 3 and the x to the 4th power are not going anywhere right now. So there's my 3, there's my x to the 4th power. Now my x to the negative 6th power is going to drop down to the denominator and become x to the 6th power. Now I encourage you not to think of this as 4 minus 6. Instead, I encourage you to think of it as canceling out. So here's a step that you didn't really need to write down, but this is what should be happening in your mind. 3x to the 4th power is like 3 and then x times x times x, alright, x to the fourth power. X to the sixth power is x times x times x times x times x times x, alright, x to the sixth power. Now, the 4 x's in the numerator are going to cancel out 4 of the x's in the denominator. So you can see how many x's are left and where they are. Okay, so that's going to be 3 over x squared. Okay, another way to think of this problem, you know how if you have x to the third power times x squared, what would that be? That would be x to the fifth power. So you're familiar with how we add these exponents when we have like bases. So another way to think of this problem, I think I'll do this in a different color. Since we have like bases, you can think of it as adding these exponents. So I would have 3, and then if I simply add the negative 6 and the 4, that would be 3x to the negative 2 power. Alright, now then, the fact that this is negative lets us know that we need to drop down to the denominator. So that would become 3 over x squared, which is what we had before. So there's just two different ways to think about it. Okay, take a look at number. Well, we have x to the third power over x to the third power. Those are definitely going to cancel each other out. So focus on this, y over y to the sixth power. So I'm hoping you can see that this y is going to cancel out one of these y's and just leave y to the fifth power in the denominator. So we'll need a 1 up there sort of as a placeholder. Remember, when we're canceling things out, like when we cancel out y over y, really what we're doing is we're making 1s. Anything divided by itself, like if I had 3 over 3 or 5 over 5 or anything over itself is going to be 1. So same thing with y over y. So it's no surprise that the numerator is going to be a 1 when everything cancels out. Okay. Alright, in order to add radical expressions, the radicand has to be exactly the same. Alright, so here I have radical 7, here I have radical 28, so at least in this form they can't be added. However, the square root of 28 can be simplified, so I'm actually going to do that off to the side. Square root, hold on, it disappeared on me. The square root of 28. Okay, so when you look at the square root of 28, what perfect square is a factor of 28? 4 is in there. So the square root of 28 is the same thing as the square root of 4 times 7. Okay, you can take the square root of 4. Alright, the square root of 4 is 2. So this 4 is going to simplify and come out of the radical because, you know, the square root of 4 is 2, not radical 2. So there's the 2 that this becomes. Now the blue part just stays the way it is. You know, if you erased the 4, you'd still have radical 7, so that's not going anywhere. So the bottom line is the square root of 28 is the same thing as 2 radical 7. And by the way, your calculator will do a lot of this for you if you're allowed to use it. So the square root of 28 is 2 radical 7, but that's what your calculator is doing. So anyway, I can take this and substitute it for radical 28 right there. So if I do that, I get 3 radical 7 plus 2 times, and here's my 2 radical 7. Alright, and yeah, this is multiplication. When there's no symbol between the two, it is multiplication. So that's why it's 2 times 2 radical 7. Okay, so you can see there's the radical 7 that we needed to be able to really do the problem. But let's do one more step first. Obviously 2 times 2 is 4, so this is 4 radical 7. Now these are like terms, so we're just going to add the coefficients. So 3 radical 7s plus 4 radical 7s, well, that's going to be 7 radical 7s. Okay, just like if you have any trouble understanding that, just remember this whole radical business works just like a variable would. If you had 3n plus 4n, most of you are comfortable with the fact that that would be 7n. So it's the same thing here. 3 radical 7s plus 4 radical 7s is 7 radical 7s. Alright, number 9. Now, when you're multiplying radicals, all you need is the indexes or indices need to be the same. So we have a cube root times a cube root. As long as the indices are the same, you can go ahead and do the multiplication. So this will be the cube root of 27 because 9 times 3 is 27. But 27 is a perfect cube. The cube root of 27 is 3. So, by the way, your calculator will do cube root, but only if it's a perfect cube, unless you want a decimal. So the way you do the cube root of 27 is first you put the 3 for cube root. And then see this symbol right here above the caret, that x root? That's the one that does it. So if you hit second caret, this becomes a cube root, and then you just type in 27. And you can see that it is in fact 3. Okay. Alright, we are asked if the following are pairs of like numbers. If so, we're supposed to do the operation, and if not, we're supposed to explain why they are not like terms. These are like terms. To be like terms, you have to have the same index and the same radicand. Alright, in other words, the same root and the same number under the radical. In fact, the only thing that's allowed to be different is the coefficient. So here I have a coefficients of 1 and 2, but they're both radical 5. So technically I should be saying, well, yes, in answer to the question, are they like terms? Yes, they are like terms. And we can go ahead and add them together. 1 plus 2 is 3. So this is 3 radical 5. I kind of slipped that in there, but yeah, radical 5 just by itself is 1 radical 5 when you think about how you would add them together. Alright, what about number 11? Well, I said both the radicand and the indices need to be the same. You see the radicand is the same, alright? It's 5 in both cases. But this is the square root, and this is the cube root. So these are not like terms. So we can say not like terms. And we'll say the indices are different. Or I guess you could say the roots are different. I'll say it the second way this time. The roots are different. Or you could have said indices. Okay, so that's number 11. Alright, for these last 4, we're supposed to identify these as rational or irrational. And if they are, we have to explain why in each case. On number 14, I hope you can see that there's a bar over here for repeating. Should make that more clear. Anyway, so let me just give a brief reminder of how rational and irrational work. All right, rational numbers, the bottom line, rational numbers are numbers that can be written as a fraction. Okay, so that's like the big definition, all right? And when I say a fraction, it's got to be a fraction of integers, okay? This would not count as a fraction. I can't say, you know, like pi over 3. Oh, that's a fraction, so that it must be rational. No, that doesn't count because the numerator and denominator have to be non-decimal numbers themselves. Okay, so any decimal, so here's some categories for you. Any number that stops. Any number that ends is going to be rational. So, you know, if I say 345, that's rational. It comes to an end. All right? I could write this as 345 over 1. And that would have the same value. So, kabam, I just wrote it as a fraction. So that makes it rational. If I said, that sort of looks like a decimal. Let me fix that. All right, if I said 0.345, this is still rational. It could be written as a fraction as well. 0.345 is 345 thousandths. Okay, and let's take a look at it on your calculator. If I say 345 over 1,000, oh look, 0.345. Okay, so any number that ends, whether it's a decimal or not, is automatically going to be rational. Okay, also repeating decimals, it turns out, are rational. Okay, for example, take the number, I'll say 0.121212 and so on. Of course, I could have written that as 0.12 with a little line over it, meaning repeating. Okay, there's a procedure that I could go through demonstrating how to write this as a fraction, but just take a look at this. If I type in 0.121212121212, okay. Alright, I just like to type in enough until it goes off the screen. If I hit my toggle key to attempt to make this into a fraction, alright, I hit too many of those guys. You see that 0.12 repeating is the same thing as 4 over 33. Alright, so look, I've got 4 over 33 in the calculator right now. If I evaluate that and make it a decimal, you can see it's the same thing as 0.12 repeating. So that turns out to be true for any repeating decimal. There's going to be some type of a fraction that you can make out of it. So any number that ends or any number that repeats is going to be rational. And certainly any number that you can just easily write as a fraction. So that means in order to be irrational, it has to be a number that does not end and does not repeat. Okay, so irrational is going to be a decimal that does not end and does not repeat. Okay, it's the opposite of the two cases that are rational. Alright, if it ends and repeats, it's rational. If it doesn't end and doesn't repeat, it's not rational. That's the bottom line. So that's why numbers like pi are irrational, because pi starts off 3.14, but it doesn't stop there. Okay, just for fun, I'm going to type pi in my calculator. Yeah, it's 3.141592654, and then I ran out of calculator space, but it really keeps on going, and there's no pattern that's going to ever repeat. And that's equally true for square roots. As long as they're not perfect squares, those are going to be irrational as well. So like, for example, square root of 7, if I put that in my calculator, okay, and again I get this decimal, it's guaranteed to go off my calculator screen, because that decimal is going to keep going forever without repeating, just like pi. Okay, so back to this quiz. Let's get up there and finish this thing off. So pi is definitely going to be irrational because it does not end and it does not repeat. I'll just put that in a text box. Does not end, does not repeat. Okay, 3.14. Notice there's no dot 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 or anything. So 3.14 is going to be rational because it ends. Any number that ends is going to be rational. So I'll just put that in a text box. Okay. Number 14 is definitely going to be rational because it repeats. Alright, if it ends or repeats, it's rational. Okay, 13 ends, 14 repeats. And number 7. I didn't mean to pick the exact example when I did it down there, but this is also irrational because, as I demonstrated somewhat, radical 7 is another number just like pi that does not end and does not repeat. Okay, and there you go. That is the end of this lesson. So students that are currently practicing for an upcoming test, please make sure that you understand every question that was on this quiz, because all this and more will be on the test. In the meantime, I will see you on the next video.